Guess it's recording now. All right. All right, I'm going to start with matter and energy questions. And the first one on the list says, which is a chemical compound? And we know we need 2 or more capital letters because a compound is a combination of 2 or more different elements. So this one has a capital and a lowercase letter, so that's the element sodium. Now this one has a plus sign. If you have a plus or minus sign, you're known as an ion, which is not a compound. A compound is neutral, so there will not be a plus or minus sign. Now here we have a capital and a lowercase, so that one is sodium. This is hydrogen, carbon, and 3 oxygens. So this would be the answer. This is a chemical compound because it's 2 or more capital letters, 2 or more elements chemically combined. Now this one has 2 ends, but it's 2 of the same element. And when you're 2 of the same element, you're a diatomic element. You're not a compound. The definition of a compound is 2 or more different elements chemically combined. So right here, there's a capital C and capital O. That's different than capital C, lowercase o, which if you went to the periodic table, you'd see that that's cobalt. And this is, again, 2 of the same elements. That's a diatomic element. And this one's just carbon. And notice they put little subscripts on this one. Little g means gas, little s means solid, little g means gas. That's just a phase of the element or the compound that's present. Okay, if they say which is pure, by definition, an element and compound are pure. So that's the answer for pure. Please just know it. And mixtures are physically combined, and it's 2 or more different substances. So it's 2 or more different substances put together. So it's not going to be pure. Now these dot diagrams, we want one pure substance only. So I said by pure, you have to pick an element or a compound. Now, that's what you want for pure. Now, if we look here, you have one black dot and one white dot, and they're all the same. They're stuck together, so that's an example of a compound, and that would be the answer. Now here, we have one white dot. That's a monoatomic element. It's one element. Now here you have 2 of the same stuck together, so that's a diatomic element. And since the 2 of them put together, it's known as a mixture. Now this one, it's a mixture of 2 monoatomic elements because you have just 1 and 1 and they're separated. Notice how choice A are stuck together to represent chemically combined. And this one also is a mixture of a monoatomic element and a diatomic element. Okay. Number 5. Which particle diagram represents only one compound in the gas phase? Okay. Now, a white dot represents one element and a black dot represents the other element, and you have to stick them together to represent a compound. Now, here they're all the same, so that can't be a compound. And here, this is a mixture, choice D, because you have 2 white stuck together and 2 black stuck together. So this is a mixture of 2 diatomic elements. I'm going to use L for elements. Now, you have to look closely. This is 1 black and 1 white, and this is 2 white and 1 black. So this is a mixture of 2 different compounds. And now this one, they're all the same, so that's why it's just one compound. Now, how do I know it's in the gas phase? Because it's all spread out. It's not stuck together. And if you look at this one, we want CO in the gas phase. This one, choice B, is solid because they're all stuck together. Now, Let me see what CO would look like. It says represent the C by a black dot and the oxygen with a white dot. So this is what I'm looking for in the gas phase. So choice A would be the answer. Here, this is just oxygen, O2. And this one has one black, which represents C, but two O's stuck together. So this is a trick because this is CO2 in the gas phase, but we don't want CO2. We just want carbon monoxide, one oxygen and one carbon. Next question, who can be broken down? Who can be decomposed by chemical change? We want a compound. Now this has one capital and one lowercase, so I know it's an element. One capital and one lowercase, so that's an element. One capital and one lowercase, so that's an element. And I told you I'm abbreviating element with EL. And this one is a compound because it's got two capital letters. And I want to tell you, all the elements are listed right here. I'm going to look up cobalt, periodic table. See, it says elements, and there's your cobalt, the CO. So they're all found on this table. That's another way you could do it. And you won't find capital CO. You'll find just lowercase co on there. Who can be decomposed? Again, we want a compound. Now we're given words. We have copper, calcium, potassium, and ammonia. So if you're given words and you don't know at this point that copper is represented by Cu, calcium is represented by Ca, and potassium is represented by K, you could go to the elements on table S and we could find calcium right here. We'll find copper right here. And we'll find potassium right here. And you will, if you go through both lists, because there's 2 pages of this, you will not find ammonia on the list. So that's what you do at this stage. You will learn ammonia is NH3 if you want to start memorizing it now, because it's a very common compound, 2 or more different elements chemically combined. Okay, next one. Who cannot be decomposed? We want an element. So we want something listed on the periodic table. So, and I know here we have 2 capital letters, 2 capital letters, 2 capital letters. This one has 1 capital and 1 lowercase. And just to show it to you, if we go to the periodic table, right here, these are the list of elements, and neon, Ne is on the list. A sample of an unknown composition was tested. The sample could not be decomposed by physical or chemical. That's the definition of an element. Now, mixtures are physically combined. Compound is chemically combined of substances. And a solution, usually you look for AQ, which means in water or aqueous. So when you see a solution, it's a mixture. And you want to look for AQ instead of a little subscript S, solid, liquid, or gas. Instead of that, you will see AQ. Okay? Which cannot be decomposed. We want an element. And again, they're given words. So I'm going to have to look up mercury, ethanol, methane, and ammonia. We already know ammonia is not it. But if we go to table S, which lists all the words, if you notice, mercury is right here. You'd have to go through all of them if you're not familiar yet with the element names, but there you go. You will not find any of these names on table S. 2 different samples decomposed. Therefore, you know they are compounds. They're not elements, because elements by definition cannot be decomposed. But it says only one is soluble in water. So they're different. They can't be the same, because if they're the same, they're both going to be soluble in water. Okay. 2 substances, A, Z, are to be identified. A cannot be broken down, so right away I know it's an element. Z can be broken down by a chemical change, so we know Z has to be a compound. Those are just the definitions. Now here they want to know one similarity between all mixtures and compounds. Well, who combines in a definite ratio? That's the definition of a compound. Compounds and elements are homogeneous. They're pure or same throughout. Some mixtures are homogeneous if it's a solution. Only mixtures can be heterogeneous. But this wants to know a similarity between all mixtures and all compounds, but they both consist of two or more substances. Which must be a mixture. I'm going to look for solution. These are just, this is a phase of matter, phase and phase, which contains only one substance. Okay. So I'm looking for an element or a compound, but sugar water has sugar and water. Rainwater has dirt and water. Salt water has salt and water. Distilled means they purified it. But by default, if you didn't know what the word distilled means, you should still be able to figure this out. Which of these terms refers to matter that could be heterogeneous? That has to be a mixture. And solutions are uniform throughout, so we're going to say solutions are homogeneous. That you should know. So here we go. We have a solution, so I'm going to pick homogeneous. And we know solutions are physically combined. You're just taking, for instance, here, salt. You're dissolving it in water. So it's a mixture. You're not chemically combining it. You could actually go to the ocean, pick up some salt water, stick it in a seashell, leave it out. Over time, the water will evaporate and there will be a white substance on your seashell. That's the salt that remains. So it is physically combined. It's not chemically combined into something new. Here's another one. A sample is prepared. You dissolve 10 grams of salt in water. So because it's dissolving, we know it's a solution. Solutions are not compounds. They're homogeneous mixtures. Okay, here we want a mixture. There's particle X, there's particle Y is represented by white dot. This is a diatomic element. This is a compound because it's two or more different things stuck together. This is a mixture of a black dot and white dot, so it's particle X and particle Y, and this is Y only according to this diagram over here. So we have our answer. Which diagram represents a mixture of elements, not compounds, elements A and B, which means we want and black and white dots together, so it's going to be Z. This one is a compound because they're stuck together, and this one is A only. How do you separate two liquids? Distillation, which means you want different, it's right in the word, boiling points, and it's how you separate L from L, liquid from liquid. A bottle of rubbing alcohol contains propanol and water. How can liquids be separated? Distillation, because DI means different boiling points. And they're combined physically because all solutions are physically combined because they're mixtures. Which property makes it possible to separate crude oil by distillation? Again, you have to just know boiling point is the definition of distillation. Distillation is when you go from vapor to liquid, liquid to vapor, because it always occurs simultaneously, and different boiling points. You're not going to pick same boiling point, so this is the answer because it says which does not involve. How do you recover a salt from a mixture? You evaporate it. When a mixture of water, sand, and salt are filtered, what passes through? The water and the salt, because only the sand is insoluble, which means it will not dissolve and it will stick on the filter paper. The salt is completely dissolved, so it passes straight through. And here's an example where we have filter paper. So you need some insoluble solid in order to use filter paper. And if you look at the choices, AQ, 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 and I see a solid here. So even if you didn't know whether it was soluble or not, doesn't matter. It's the only choice with the solid. A mixture of crystals of salt and sugar is added to water and stirred until all solids have dissolved. So we know it's a mixture. And we said mixtures are homogeneous and they cannot be separated by filtration because it's completely dissolved. And since it's dissolved, it will go through the filter paper. Now, chemical versus physical property. Now, rust is the key word for chemical, so I'm done. Whether it could be flattened or whether it conducts or whether you could, this is called ductile when you draw it into a wire. Those are all just physical attributes of a metal. Which describes a chemical property. I'm looking for keywords like burn, rust, corrosion, so I'm done. But whether it dissolves or the color or the melting point, those are all physical changes because you want to make sure you're familiar with physical versus chemical. Which is the chemical property of oxygen? Well, whether it could be smushed, that's a physical property. Whether it's soluble, we already said that that's physical. You just, because then it would be a mixture. Melting point, that's the temperature at which it melts. That's a physical property. But here we go. When we combine to produce a compound, we said that's a chemical change because you turn into something new. And another key word for chemical change is react. React, form a compound. But whether you form a solution, that's a physically combined, that's a mixture. So here they want a physical property. So you have to know forming a solution is a physical property. Just looking at this substance here, I know it's a compound because it's two or more different substances, two or more different elements chemically combined. Now, we want a physical change. So when you think of a physical change, you're going to think of a phase change. So here, because they're all spread out, we're going to assume it's a gas. Now here, it's the same. It's black and white, but they're closer together, so this is probably a liquid. This one turned into a new compound because before it was just one white and one black. This is definitely turned into something new. It broke up into its diatomic elements, and here it broke up into monatomic elements. So these are chemical changes because it turned into something new. So the only one that's physically changing is going from either solid to liquid to gas or any of those. So this one was a tough one. Which is a chemical change? I'm looking for keywords rust, burn, corrosion, react. Whether it melts, that's going from solid to liquid. That's a physical change because I said a phase change is a physical change. Evaporates going from liquid to gas. Once again, it's a phase change. Crystallization is liquid to solid. So again, that's a phase change. How do we do chemical change? Well, I see bubbling. A cool shiny metal is added to water and bubbling occurs. So that's something new formed, like in this mixture. Now here it's saying ethanol is added to an empty beaker and it disappeared. That meant it evaporated, turned into a gas, and we know a phase change is a physical change. And then here, a solid is heated and turns into a liquid. Once again, that's a phase change, which is physical. Here, large crystals are crushed. Crushed is just a physical change again. What type of change must occur to form a compound? Chemical change. Which is exothermic? Well, melt is solid to liquid. Vaporization is liquid to gas. Freeze is liquid to solid. And sublime is skip the liquid. So you're going from solid to gas. Well, we could do oddball rule. Let me do solid, liquid, gas. Solid to gas goes that way. Liquid to solid goes the opposite. Liquid to gas, if we're looking at this chart, is going this way. Solid to liquid, if we look at this chart, is going this way. So there's your oddball. But the freezing of water is the cooling curve. All the other ones are the heating curve. And the cooling curve is the exothermic reaction, which is endothermic. I could do this again. Condensation is gas to liquid. And deposition is gas to solid. So if you look at this chart again, they're both going that way. Now here, melting and freezing, they're going opposite ways. Melting is going from solid to liquid, which is going this way. And freezing is going that way. So they're going opposite ways. So that's just silly. Condensation, again, we saw as gas to liquid, so it's going that way. And sublimation is solid to gas, so it's going that way. They're opposites. But melting is solid to liquid. It's going this way, solid to liquid. Evaporation is liquid to gas. That's going that way. That's the heating curve. And you have to know the heating curve is endothermic. What form of energy is converted to thermal when propane burns? Burn is a chemical change. Which transfer of energy occurs when ice cubes are placed in water that has a temperature of 45 degrees? Well, we have to think that ice is 0 degrees Celsius because it's water. And if you have water that's 45 degrees, heat always flows high to low. And heat energy is known as thermal energy. And you're going from high to low, so from the water to the ice. Okay, so that's a concept you have to know. Heat always flows from hot to cold. Two samples of gold have different temperatures are placed in contact with one another. Heat will flow from a gold at 60 to a sample of gold that is 50 because you have to go from high to low. Notice 80 is higher than 60, 70 is higher than 60, and these are the same. As the temperature decreases, average kinetic energy decreases because by definition, temperature is the average kinetic energy. Take. So it's like saying if something goes down, then that something goes down. It's just saying the same thing in another way. Okay, now they're both at 1 atmosphere and 298 K. So they're both at 298 K. So they're both at the same temperature. 1 mole of this and 1 mole of that. Right now, you don't even know what a mole is, but it's just the same amount, obviously. But I don't think that's a fair question to ask in the beginning of the year. But anyway, you have water liquid, and this is ethanol liquid. What do they have the same? Well, temperature, because they're both at 298 K, and we said temperature means average kinetic energy. An increase in the average kinetic energy occurs when increase in T4 temperature. Now, what Celsius temperature is equivalent to 418 K? Well, we're going to go to table T, and right at the bottom of table T, Kelvin is Celsius plus 273. So we could go Kelvin equals Celsius plus 273. And they gave us Kelvin, so I'm going to plug in right here. So in order to solve for Celsius, I have to get rid of 273. And then we're going to subtract. 8 minus 3 is 5. And then we have 11 minus 7 is 4. Of course, you have your calculator. And there's the answer. 145 degrees Celsius is the answer. Okay. Archimedes, a Greek inventor and mathematician, made several discoveries important to science today. According to legends, to find out if the royal crown was made of gold only, the king suspected that the crown consisted of a mixture of gold, tin, and copper. Archimedes measured the mass of the crown and the total amount of water displaced when it was completely submerged. He repeated the procedure. He was able to determine the crown was not made entirely of gold without damaging it. What's one physical property he used? And its density. Hopefully you all know this story. It's like if you have a bunch of liquid and then you put the crown in, what happens is because the crown is going to displace the water, which means move it up. So you actually, like if this was 10 mLs and now it went up to 15 mLs, then you know that the volume would be 5 mLs because that's how much it displaced from, you know, the original was 10. That's how much it moved up, and that's how much space it took up. Anyway, I don't know when you're going to do density. This might not be in this section, but since it's on here, we're going to cover it. But that's it. Determine the volume of a 75-gram sample of gold at STP. Now, you might say, how do I do that? Well, if you look, the first equation on table T, which you're given on the Regents, is density, which includes a volume, density, and mass. So we have mass, which is 75 grams. We want the volume, and because it's gold, we could actually go to the periodic table, table S, and look up gold. And let's see, density is this column here, grams per centimeters cubed. And here it is, 19.3. So basically, we know the density is 19.3 when we have the grams. So to solve, you're going to cross multiply. So you're going to do 19.3 times x equals 75 times 1. And then you divide 75 by 19.3. And you get 3.89. That's what we can round it to. Centimeters cubed. You don't need units. It's not asking for them. Which diagram best represents a gas in a closed container? Well, this one looks like a gas to me. These are close together, so I'm going to say liquid. These are close together. I think all the other ones are liquids. Why are they not solids? Because a solid is a regular geometric pattern. They'd be all stuck together like that. Which grouping of the three phases of bromine is listed in order from left to right for increasing distance? Well, increasing distance, well, let's talk about a solid. A solid is close together. Then you have a liquid, which is a little bit far apart, so it's increasing distance. And then a gas is really far apart, so that's increasing distance between the molecules, solid to liquid to gas. Next one, which 5 ml sample of ammonia, you're going to learn NH3 is ammonia, will take the shape and completely fill a container? As soon as I say completely fill a closed container, I know I'm looking for a gas. So I have to look at the subscript here. This is solid. This means it's a solution in water, and that's a liquid. Which correctly describes a sample of a gas? Crystalline is definition of solid. Regular geometric pattern is a solid. Takes the shape and volume of any container, that's a gas. Definite amount of liquid and takes the shape, that would be a liquid. Because a gas does not have a definite volume. It takes the volume of whatever. Like for instance, if you have different balloons, it takes the shape of whatever balloon shape you put the gas in. At 101.3 kPa and 298 K, at this point you probably don't know what that means, so we could ignore it. Which element could this represent? Well, to me it looks like a solid, so this is not a fair question either, because you have to know which phase each element is at this temperature and pressure. But if we look at the periodic table, we have xenon, radon, krypton, and I'm going to show quickly. Xenon, radon, and krypton are all in this last column, and it's known as a noble gas. These are all gases at that temperature. And then we have Ag, which you're going to learn is silver, and silver is a metal, and metals are solids. There's only one metal that's not a solid, and that's mercury, and that's a liquid. Which material the particles arranged in a regular geometric pattern? We want to look for subscript S for solid. So it doesn't matter who the compound, what compounds they are, the key is solid. Which sample contains particles in a rich, fixed geometric pattern? Solid, I'm looking for, right there. Which element is a solid? Again, you have to memorize the 7 diatomic elements in nature. They exist as twins, and you're going to memorize that iodine is the solid, but it spells the word is. That's how I'm going to remember that. All the other ones here are gases. There's one liquid, which is bromine. You're going to memorize bromine is a liquid, iodine is a solid, and the rest of the diatomic, the 5 diatomic remaining, are gases. Heat of fusion is just a definition. It's solid to liquid. So again, I'm just looking at the subscripts. As ice melts, okay, so you're going from solid to liquid, so you're adding heat. If you're adding heat, the potential energy, which is stored energy, still increases. Next one, the solid and liquid phases of water. So if water is going from solid to liquid, it's the melting point. You have to memorize the melting point of water is 0 degrees Celsius or 273 K. That's just the definition. Here again, solid to liquid water is the melting point, which is 0 degrees Celsius, which I don't see, or 273 Kelvin. I am not going to go over heat problems right now. That's going to be a separate chapter. So I'm going to move on, which is the release of energy. Well, normally I'm going to say solid, liquid, gas. So here, solid to gas is going this way. Gas to liquid is backwards. Liquid to gas is going this way, the way I wrote it. And solid to liquid is going this way. So I have oddball, or you can know it's just the cooling curve, which is exothermic. Let's see. I'm going to write solid to liquid to gas. Solid to gas is going this way, so it's endo. Solid to liquid's going this way, it's endo. Liquid to gas is going this way, endo. And gas to liquid is backwards. That's the cooling curve. Now here it is the heating curve, starting as a solid. So I'm going to label solid, liquid, gas. Which line segment represents an increase in potential energy, but no change in temperature? Because average kinetic energy means temperature. When there's no change in temperature, it's a flat line. So you're looking for B, C, or DE. And DE is not a choice. Here's another one, which is an increase in average kinetic energy, which is temperature. So I want a diagonal line as an increase in temperature. So AB and BC is out, DE is out, BC is out, AB and CD. There you go. That's because there's temperature in here. It's going up. Okay, here's the substance starting as a solid. Solid, liquid, gas. What's the melting point? That's going from solid to liquid, so I got to go over here. So it's below 60, so the only answer could be 55. When they want the melting point, they want the degrees Celsius from the chart. Next one, draw nitrogen as a gas. Okay, well, they're saying that's one molecule, so I just have to show them further apart. Liquid, I'm going to have them closer together, but not in a regular geometric pattern. A solid would look like this, where they're all neatly organized. Okay, but we want 6 molecules. I didn't draw 6. 1, 2, 3, 4, 5, 6. I'll draw an extra one, and here I only have 3. What's the difference with particle arrangement? You could say the gas is further apart. I'm going to say increasing distance between the molecules. What's the limitation of a two-dimensional model? You could talk about that it's a 3D world. This is just a simple question that it doesn't truly represent how it looks in space. We're not doing heat problems. Okay, vapor pressure. This shows the pressure coming off of vapor. I guess when it's going from liquid to gas, possibly. According to the diagram, what's the vapor pressure of liquid A at 70 degrees? Go to 70 degrees. Go to A on the line. You go over here. And what is it? 700 pressure. One of the units for pressure is millimeters of mercury. Next one. What temperature does liquid B have the same vapor pressure at A at 70? So we want the temperature of B at this vapor pressure. So I'm going to go down. And it's definitely more than 110, less than 120. I might say like 113 or something like that. You have leeway. Which liquid in the given diagram will evaporate most rapidly? Well, A is first here. So A is the one that turns into a gas first. And if it says when you evaporate, you have weaker, I'm going to write intermolecular force like this. And anyway, when you boil first, you have weaker forces between the molecules. That's why you're turning into a gas. Why the vapor pressure of propanone increases when temperature increases? Because when you have an increase in temperature, the particles move faster. And if the particles move faster, you're increasing of it going from liquid to gas. You're increasing the pressure. It's a direct relationship. If the temperature goes up, the pressure goes up. You could even just say it's directly related. A liquid's boiling point is the temperature at which a vapor pressure equals the atmospheric pressure. Using the vapor pressure for liquids reference table, what's the boiling point of propanone at 70 kPa? So let's see, 70 kPa. I have to go here. I'm like, what is that? 50, 60, 70, 80, 90, 100. I want to make sure. So 70, and I want propanone. Propanone's the first line on the list. So I'm all the way down here. These go by tens. Now here I think it goes by fives. Let's see, 30, 35, 40, 45. So the answer here is 45 degrees Celsius. Cooling curve. Starting as a liquid. Very important you read that because normally you don't think to put a gas there, but it's a piece of the curve. It's not the whole cooling curve chart. Which line segment is a phase change? Well, BC, because you're going from liquid to solid. What's that melting point? Well, you go over here. It's, I would say, about 42 degrees Celsius. Again, you could give or take a point or two and you'll still get the same, you'll get credit for it. At which point do the particles have the highest average kinetic energy? Average kinetic energy means temperature, so it's point A. Name the phase change. Well, it's going from liquid to solid, so you could say crystallization, solidification. There's plenty of answers here that you could say. Next one. Sample water is heated from a liquid, so we're not labeling it solid. It's liquid to gas. And this is the phase change going from liquid to gas. That's what they want you to label. For section QR, that's the diagonal. What's happening in the water molecules? You could say that the temperature is going up, heat is going, stored energy is going up, and the potential energy is going up. But during RS, which is a plateau, you're still adding heat. So stored energy still goes up, but the temperature is constant because the thermometer stops moving. Next one. What's the melting point? Now let's see. It's starting as a substance above its boiling point, so it's gas, liquid, solid. This is the full complete curve. What's the melting point? That's going from liquid to solid, so that's right there, and it's exactly on the 50 degrees, which is the gas phase only. We said that was AB. Now this one's starting as a solid, liquid, gas. What's happening to average kinetic energy? That's temperature during BC. Well, it's a plateau, so we say temperature is constant. It does not change. How does the heating curve illustrate the heat of vaporization is greater than the heat of fusion? Well, heat of fusion is solid to liquid. Vaporization is liquid to gas. And if you see DE is a longer line, that's how you show that it's greater. It has a longer line than that line. Identify the process that takes place during DE. Well, I have to see it starts as a solid, so that's solid, liquid, gas. So this is called vaporization or liquid to gas. Identify a line segment where average kinetic energy, which is temperature, is increasing. I could say AB, I could say CD, and I could say EF. In math, you put a line over a line segment. I don't think in chemistry they're really going to care. You could just write AB. What's happening to X during BC? You could say, it says to include the word energy or particle behavior. So I'm going to say average kinetic energy is constant. This way I included the word energy. There's plenty of things you could say. You could say it's undergoing a phase change. Use that dot to represent the substance. Draw 5 particles as they would appear in point F. Well, point F is a gas, so I'm going to have them all far apart, not touching. Now, here, a substance is a solid at 15 degrees. Okay, now temperature goes up to 65. So let me see if I went by 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. I'm going to do that. I'm just going to graph this before I even read it. 0 is at 15. 1 is at 32. So I'm just going to put it in here. Then that's 35, 40, 45. So next one's like right here. 20, 25, 30, 32 here. Okay. Now 4. 2 is at 3 is at 53. If that's 55, 1, 2, 3. I'm going to put over here. 4 is at 53. 5 is at 53. If you notice, I don't even know if I'm at 7 now. I'm at 8. All the way through 10, it's the same line. And then 11 went to 60. And 12 went to 65. There you go. There's my graph. I didn't do a good job connecting it, but that's all right. I just graphed it. Plot the data. How do we know average kinetic energy is increasing during the first 3 minutes? Well, you have to know what average kinetic energy means. It means temperature. So you could see because the temperature is going up. And then what's the melting point? Well, that's where it's constant. It has to be where 53 degrees Celsius, where it's doesn't change the temperature. And that's basically the first part of matter and energy. There's also something where you have to find calories or joules, and then there's gas laws. That's usually part of this unit. I'm going to do that separately, so I hope this helped. And yeah, I'm going to end it here.